Today we are going to learn about the Thevenin's theorem. The Thevenin's theorem states that a linear two-terminal circuit can be represented by an equivalent circuit consisting of a voltage source in series with a resistor. Given this circuit can be divided into a fixed part and also a variable load. The variable load can be changing from time to time. For example, it is lights. During the night time, it is turned on, while during the daytime, it is turned off. The fixed part of a circuit can be represented by an equivalent circuit, which is called the Thevenin's equivalent circuit. The Thevenin's equivalent circuit has a voltage source called the VTH, the Thevenin voltage, in series with the Thevenin resistance. Let's see what is the benefit of the Thevenin's equivalent circuit. So for this question, we want to find the current IL passing through the load RL when RL keeps changing from 1K, 2K to 3K ohms. We can find the current IL using the original circuit. But the original circuit has 3 mesh loops. So for question 1, when RL is equal to 1K, we will have to do 3 simultaneous equations. And for question 2, we have to do another 3 simultaneous equations. And then for question 3, we have to do another 3 simultaneous equations. When we simplify the fixed part of a circuit to the Thevenin's equivalent circuit, there is only one loop. We can use V equal to IR, so I equal to V of R, to find the current IL. So we just need to change the value of RL from 1K, 2K to 3K ohms for this Thevenin equivalent circuit to find the current. Therefore, the benefit of the Thevenin's equivalent circuit is that we don't need to keep repeating the complex calculations. What we need to do is just use the Thevenin voltage and the Thevenin resistance to represent the complex circuits. Other than simplifying the fixed part of a circuit using Thevenin's theorem, we can simplify the circuit using Norton's theorem. The Norton's theorem states that a linear two-terminal circuit can be represented by an equivalent circuit consisting of a current source in parallel with a resistor. Let's look at this circuit. The current source IN is called the Norton current, is in parallel with the resistor, which is called the Norton resistors, Rn. You can see that the Norton's equivalent circuit can actually be transformed to the Thevenin's equivalent circuit using source transformation. The resistance value, 500 ohms, is the same before and after the source transformation, which means that the Norton resistance is also equivalent to the Thevenin resistance. Let's determine the Thevenin and Norton equivalent circuits at terminals A to B for this circuit. To find the Thevenin voltage VTH, we just copy the original circuit and find the open circuit voltage VOC at terminals A to B, where the Thevenin voltage VTH will be equal to this open circuit voltage VOC. To find the Norton current IN, we have to copy the original circuit but short circuit the terminals A to B. We will have a short circuit current ISC. This ISC is equal to the Norton current IN. Let's do some circuit analysis to find the Thevenin voltage VTH. We will start by applying a nodal analysis at node V1. You can also do mesh analysis, but nodal analysis will be easier for this question because we only need one node V1 to solve the question. However, If you do mesh analysis, you will require 2 loops. The summation of current flowing out of a node is equal to 0. This is nodal analysis. Let's apply nodal analysis at node V1. At node V1, there are 3 currents flowing out. That is, one to the left, another one downwards, another one to the right side. Okay? So let's find the current flowing to the left side. The current flowing towards the left is a V1 minus 12 divided by 1K. While the current flowing downwards is equal to negative 10 milliamperes because IS is positive upwards. So the current flowing downwards will be negative 10 milli. The next one is the current flowing to the right side. We will have V1 minus the reference point, which is 0, divided by the resistance 2K plus 4K. The current flowing through the R3 is equal to 0 because of open circuit at point A to B. After finding the voltage V1, we can find the open circuit voltage VOC using a voltage divider rule. This VOC will be equivalent to VR4 because the voltage of R3 is 0. So voltage divider rule is the resistance of the R4 divided by the summation of the resistors in series. That is 2K plus 4K multiply a voltage V1. So the open circuit voltage is equal to 12.57 volts. The Thevenin voltage VTH will be equal to the open circuit voltage VOC. Now let's find the Norton current IN. To find the Norton current, we short circuit A to B. Then we got ISC, where ISC will be equal to the Norton current. To find ISC, we apply nodal analysis at points VA and VB. Take note that I label this node as VA, while I label this node as V1 because they are different circuits. To avoid confusion, I label this as VA and this as V1. After applying nodal analysis at points VA and VB, we got 2 equations with 2 unknowns VA and VB. Therefore, we can find the values for VA and VB. To find the short circuit current ISC, the value will be equal to VB minus 0, the reference point, divided by the resistance 3K. Therefore, we got our ISC as 3.1 milliampere, where the Norton current is equal to the short circuit current equal to 3.1 milliampere. The Thevenin resistance and also the Norton resistance is equal to the open circuit voltage VOC divided by the short circuit current ISC. That is also equal to the Thevenin voltage divided by the Norton current. Then we will be able to get 4,700 ohms. There is another method to find the Thevenin's resistance and also the Norton resistance. So this method 2, we set all independent sources to 0. When we set the voltage source to 0, it is like a short circuit. When we set the current source to 0, it is like an open circuit. Therefore, for method 2, we short circuit the voltage source and open circuit the current source. After short circuit the voltage source and open circuit the current source, we can have this simplified circuit. This R1 and R2 are in series, we can add them together. And then this R1 and R2 is in parallel with R4. We can find their parallel resistance, R parallel. And then we add this parallel resistance with R3. Therefore, we get the Thevenin resistance or Norton current resistance equal to 4700 ohms, same as method 1. After we found the Thevenin voltage VTH, the Norton current IN, and also the equivalent resistance RTH and RN, we will be able to draw the Thevenin equivalent resistance and also the Norton equivalent resistance. So get back to our very first question to find the current IL passing through the load RL, okay, when RL keeps changing from 1K, 2K to 3K. So with Thevenin equivalent circuit, we can just simply substitute the value of RL, keep changing that value of RL to find the IL. Same to Norton equivalent circuit, we can just change the value of RL to find the IL. However, when there is a dependent source, for example in this circuit, there is a dependent source 1.5 Vx, we cannot set this equal to 0 because it is dependent on the circuit variables. So in this case, this 1.5 Vx dependent source is dependent on the voltage of R1. Alright? We can set the independent source equal to 0, but not the dependent source. So we set all the independent sources to 0 while leaving the dependent sources there. We cannot use the simple method like method 2 to find the resultant resistance because there exists a dependent sources in this circuit. So to do so, we add a voltage or a current source between terminals A and B. So in this case, we add a voltage source between terminals A and B. This voltage source VO, we can set to any value. So in our case, we set it to 1 volt. You can also set to 1.5 to 10 volts, whatever value, alright? After adding the voltage source VO, our task now is to find the current passing through VO, that is to find IO. To find the current IO, we apply a nodal analysis at point VA and VB. We use a supernode analysis to find the VA and VB. So let's look at here. VA minus 0 divided by 1K is the current flowing in this direction. And then there's a current flowing this way. And then this current is splitting into here, this tree. So we get VB minus 0 divided by 4K. And then VB minus 1 divided by 3K. While this one is a current flowing in the right direction and also a current flowing in the left direction. They are cancelling off each other. So this is a supernode analysis. The next equation we can get is the VA minus VB equal to negative 1.5 Vx. And then another equations we can get is a VA minus 0 equal to negative Vx. After getting these three equations, we will be able to get the three unknowns. So our VB equal to negative 0.2353 volts. To find the current IO, we get VB minus 1 divided by 3K will be the current flowing in this direction, while our IO is in opposite direction. So this VB minus 1 divided by 3K will be equal to negative IO. Then we can solve for IO, right? Then our Thevenin resistance and also the Norton resistance will be equal to this VO divided by IO. And then we can get 2428 ohms. Let's check if we are able to find the Thevenin and Norton resistance using the method 1. Alright, that is VOC divided by ISC. Okay, so if we find the Thevenin voltage using Nodal analysis or mesh analysis, we will be able to get the Thevenin voltage equal to 8 volts. While the Norton current, when we short circuit the terminals A and B, we will be able to get the Norton current equal to 3.29 milliamperes. So we get VOC equal to 8 divided by the ISC 3.29 milliamperes. We'll be able to get the same Thevenin and Norton resistance 2428 ohms like previously. Let's summarize what we have learned today. So to find the Thevenin voltage, we find the open circuit voltage. To find the Norton current, we short circuit the terminals A and B to find the short circuit current, ISC. Okay, so to find the Thevenin resistance and also the Norton resistance, we get the Thevenin voltage VTH divided by the Norton current IN. Alright, this will be able to solve our problems. Alternatively and optionally, we can use method 2 to find the Thevenin and Norton resistance by short circuiting the voltage, the independent voltage source, and open circuit the independent current source. Alright, so in case there is a dependent source, we must not open circuit or short circuit the dependent source. This leads to method 3. We need to do what we did in method 2 and also add a voltage VO at terminals A and B. Alright, and then we divide VO divided by IO to get the Thevenin and Norton resistance.